Hello and welcome back. I know it's not considered polite to ask someone their age or dig into the past, but I don't think the Earth will mind. Today, we'll be digging into the Earth's history and discussing geological time. The geological timescale is continually being updated and is maintained by the International Commission of Stratigraphy. By studying rocks and using different techniques, such as analyzing fossils to date the sedimentary rock, along with a range of isotopic techniques, we can determine the actual age of igneous and metamorphic rocks. I'll not go into too much detail about isotopic dating, but want to mention this technique. Isotopic dating is based on the fact that we know the decay rates of some unstable isotopes of elements, which are constant over time. A common isotope that is used in geology is the decay of potassium-40 to argon-40, and has a half-life of 1.3 billion years. When looking at isotopic dating, we look at an isotope's half-life, which is the time it takes the element to decay by half. In addition to isotopic dating, it is important to mention a few basic principles that have been used for arranging events before there was a way of actually establishing any numerical age of a given rock. There are a number of notable geologists to mention that have aided in the principle of faunal succession, which was proposed by William Smith and is based on the observation of sedimentary rocks and studying fossilized fauna and flora. This principle allows us to identify and date rock and strata, layers of rock, because there is a defined order in which organisms have evolved over time, and by identifying a specific fossil, this can be used to identify the age of the rock. And I wanted to highlight some geologists that contributed greatly to this field during this time, which were Mary Anning, Ethel Bennett, Elizabeth Anderson Gray, Mary Lyell, and many more. I want to spend a brief moment highlighting some contributions that these women have made to geology, since women contributions are not talked about much, especially during this time. It is important to highlight the contributions because they paved the way for other women in the field. Bennett was an independent geologist and is commonly referred to as the first lady geologist in Britain. She was a pioneer biostratigrapher and contributed greatly to the field. In particular, she even published her own work and corresponded with other prominent male geologists during this time, which was uncommon and unheard of. She had an extensive fossil collection and donated many species to public museums to help benefit science. Another woman in geology I wanted to highlight from the 19th century was Mary Anning, who was a well-known fossil hunter and discovered an assortment of skeletons, including the first Ichthyosaurus and Pterosaur. She was a notable fossil finder and was often neglected in publications by the male geologists whom she sold her fossils to. Both Bennett and Anning had knowledge about the principles of stratigraphy, which is the branch of geology that is concerned with studying rock layers. Bennett was a larger contributor to the conversation and debates with male geologists and didn't always agree with William Smith. The naming of geological time periods are often named after the area in which the rocks were discovered, such as the Jurassic being named after the Jura Mountains in France and Switzerland. In some cases, they are named after rocks that were common for that age. Another principle I want to mention as well is the principle of superposition, which is a way to relatively date strata by the older strata being located at the bottom and the top layer being the most recent. As you can see, this is a very simple way to determine what strata is old and new by looking at the layering. Any disruption to this layering is a result of tectonic processes, such as an earthquake or other tectonic disruptions. The principle of inclusion states that any rock fragment or class that is found in a sedimentary rock, then this inclusion must be older than the rock it has been included with. Another important principle is the cross-cutting relationship, which is when you have a geological feature that has a cut or some sort of disruption in it, which must be a younger feature. It is important to also bring into the conversation unconformities, which represent gaps or interruptions in geological records and occurs when rocks or sediments have eroded away. This is similar to if you were reading a book and all of a sudden you are missing a page, but instead we are missing a record of this geological time. If I was reading a book, I would be devastated if I was missing pages. However, for geologists, these unconformities actually gives a geologist important information that can indicate a number of things, such as a change in ocean levels, erosion, or any deformations. 3 types of unconformities are as follows. Nonconformity is a boundary between non-sedimentary rock and sedimentary rock. This could be a boundary where sedimentary rock lies above igneous or metamorphic rock. Angular unconformity is where a boundary between two layers of sedimentary rock, where the horizontal sedimentary rock has been deposited on top of rock that has been tilted or folded. This conformity boundary is an erosion layer that separates two sets of rock layers. This boundary can sometimes be hard to identify. Geological time is separated into 4 eons: Hadean, spanning 4,570 to 3,850 MA, Archean, spanning 3,850 to 2,500 MA, Proterozoic, spanning 2,500 to 540 MA, and Phanerozoic, spanning 540 MA to now. The first 3 eons comprise of 90% of the Earth's history and are collectively referred to as the super eon known as Precambrian, with the eon Phanerozoic means visible life and is one eon that we are most familiar with since we are living in it. We can now break down this eon into eras, periods, epochs, and ages. The Phanerozoic eon is divided into 3 eras: Paleozoic, which means early life, Mesozoic, which means middle life, and Cenozoic, which is new life. Each of these eras are further divided into periods. I wanted to focus in on the Cenozoic era since this is the most current one, which has 3 periods: Paleogene, Neogene, and Quaternary, and 7 epochs. At the start of the Cenozoic era is when dinosaurs became extinct, which is not a coincidence that the boundary between the Cretaceous period and the Paleogene period is the exact moment that coincides with the massive extinction. The boundary between these 2 periods is marked by in the sedimentary rocks that shows the fossil records and the division of organisms in the Cretaceous period, the Paleogene period. The Earth was very warm up until the earlier part of the Eocene epoch, after which the Earth began steadily cooling. The first glaciers appeared in Antarctica during the Oligocene epochs, and then they slowly began covering varying parts of the world, including North America and Europe, up until the Pleistocene epoch. And the epoch that we are currently in the most current, is the Holocene epoch. And this covers approximately the last 11,700 years of Earth history. Thank you for joining me on today's discussion, where we talked about some basic principles of relative dating, historic figures, and the contributions to science, and how unconformities play a large role in filling the gaps, and geological time. Until next time, have a wonderful day.
1, 2, 3.